All right, so we're going to go through the workflow with mechanical APDL with this EVO fender here in Advanced Material Exchange. So here we are in mechanical APDL. We have the model defined, and what we need to do now is write out a CDB file. We're going to use the CD write command in Ansys to do this. So I'm going to give it the CD write command, and then I'm going to define the file name as well as the path that I want to write it to. So here you see I've highlighted the file name, and we're going to use the extension CDB. Hit enter. It'll export that file, and then I'm going to import the CDB file into Advanced Material Exchange. Ansys, or AME, supports many Ansys types, file types, CDB, INP, and DAT. So here we have the model. We're going to select our unit set and bring that model into Advanced Material Exchange. And then we're going to import the mold flow model so that we can transfer all the fiber orientations and material properties from the mold flow mesh to the structural mesh. Both models are side by side now. You can see the meshes are different. We're going to map the results from mesh to mesh, and you'll see that it'll bring up a plot of the fiber orientations. And the mold flow model is a midplane model, the structural model is a shell model, so we can actually step through the different shell locations, top, middle, and bottom. And the colors are a little bit off here because our structural mesh is pretty coarse. Now I'm going to choose my material type, which is elastic plastic, and I'm going to define the nonlinear behavior by reading in a CSV file, which contains all of the data that we need. And we're just going to plot the data. And plotting the data will allow us to fit our theoretical curves to the experimental data so we can use our theoretical curves in the structural simulation. We'll choose our environment, which is the temperature down here, close it, and then all we need left to do is export the new CDB file for use in an Ansys analysis. So now we're on our desktop. You can see I'm in a working directory, and I've highlighted those files we exported. I'm going to open up a utility that comes with Helios PFA called the command shell. And when I open the command shell, I'm going to navigate to the folder where I've put those CDB files, and I'm going to type a simple command called Ansys Helios, which basically tells Ansys to use Helios PFA during the solution. The correct syntax is being highlighted on the screen here. So it's Ansys Helios, the version number, and then the file name. So we're going to use 15.0, and then I'm going to give it the file name, which is the Fender Manual BCs 2 AME with the CDB extension. Hit enter, run it, and then I can just read in the RST or the results file when I'm back in mechanical APDL. So this is that RST file. I'm going to read results by pick, so I'm going to choose increment 46 out of 50 during my nonlinear analysis. And then I'm going to plot the total displacement. So this is a nodal solution, and I want to understand what the displacement looks like here. And this is at increment 46. We could obviously step through the other increments and watch the displacement accumulate as we continue to load it. This is basically just a simple pressure load where we're pushing in on it like somebody putting their knee on it, and the fender's constrained like it would be in the car. And now I'm going to plot what we call SVAR11, which is a solution-dependent state variable, and Helios outputs these. The only way to plot them in mechanical APDL is with the syntax shown on the screen, with the PLN sol SVAR11. And this is a form of the matrix effective stress. And then I'll output SVAR9, which is the matrix tangent modulus. Red is no failure, blue is tons of plasticity or low tangent modulus.